Okay, so it is time for class. We had a pre-lecture due today. On Friday, Lab 4 is due, and we'll have the Lab 4 quiz. The last pre-lecture is next Tuesday. Homework 11 will be due. You have 2 homeworks due next week. One is on probably only one of the homework 12 is on DACs and ADCs. Homework 11 is back on the frequency response stuff. No lab next week, and our final exam is Wednesday, April 25th from 3 to 5 p.m. Now, you can turn in your course evaluation. I've got a list here of, one person has turned in their course evaluation in this class. Please do that. It's worth 5 extra credit points on the final exam, or it could be your ticket out of the final. There is a practice final posted to BB Learn along with the solution. I got kind of tired working it. It's a new practice final this semester. And there's a couple places in there that it says literally, I am tired. Go see homework 6, number 5 solution, okay? Homework 11 there's 30 bonus points on the next 2 homeworks. And I will take 1 week worth of late lab to my email by 4/23. I want them in before the final exam. Now, if you want to be exempt from the final, you must have an 88% or greater overall average. And yes, I will call that an A. For the rest of you, that means if you manage to pull your average up to an 88, you've got an A. You must turn in a completed lab 4 on time, and you must do the course evaluation. Test scoring. Believe it or not, at the end of the year, there's a committee, this is a university, there's a committee that's going to go through and read all my course evaluations and give me a raise based upon them or not. It's usually or not, because there's years we just don't get raises. Nobody gets raises. But I just like to kind of keep that up. $490 for the fall. You can register for it. There are people who are registering now. Of course, there's time conflicts with both the 348 lab and the 364 lab. It's like 10 minutes, so I'm doing all these time conflict overrides and just saying you got to leave the lab early. So this is kind of like the hands-on elective. The signal considerations you need to do a printed circuit board design and to hook 2 ICs together successfully. And we'll do a lot of actually doing stuff on the board, breadboards, doing a simple PCB design, just so that you go through the process once. Also, EE380 is Daphne Chen's device physics class. That's going to be offered in the fall again. That's a really good one if you want to work in the semiconductor industry. And pretty much $490 in the fall, I mean, it's like across the board if you end up being a test engineer and that's mostly where people start out. It's kind of like the good stuff you need to get started. So, and I'd rather teach that than whatever EE215 they keep throwing at me. I told him I don't want to teach C programming, so he goes, you made me fill out this Excel spreadsheet that has this like list of classes that you regularly teach, and so I wrote down 283, 84, 90. Pick any 2. I'm only going to be here part-time. I don't care. My most of my caring from now on is going to be geared towards the work I'm doing in the physics department for my PhD. But I still care about you guys. I always care about the students. I just don't care about management. I'm recording. I've always put you guys first. Okay. We're going to look at finish up the DAC architectures and start some of the ADC architectures. On Tuesday, what we're going to do is finish up the ADC architectures and look at some basic specifications on ADCs and DACs and how they're calculated. So what happened here? There's a missing slide. I deleted the wrong slide. Okay. So this is, now I'm really upset with myself. Let me go back to this one. We'll be in here. We'll flip slides and this will ultimately confuse me. Whatchamacallit? We're back. Oh, I got it right here. This is the R2R DAC. It's a little bit more difficult to, oh, you can't see anything. Yeah. I gotta push some buttons, sorry. I'm talking like everybody can see my computer screen. And wait for it. And I can't even push the button until, okay, there it goes. Now I can push the button. Okay. Take a technology break here. Okay. So this is the R2R DAC. It's a little bit more difficult to analyze. We'll kind of go through this piece by piece as we go through it. This is the slide I wanted. We could just do a Thevenin equivalent of the whole thing. We could do a superposition of sources. There's a lot of things we can do, but we're going to kind of like go through this, and I'm going to show you the tricks that make it really easy to do. And one of your practice final exam problems is based off of this stack. There's only 2 resistor values in here. Look at this. They're all either R or 2R, except for the one I gave you on the practice final, which one of them's 3R. It has gain. I didn't need to do that. The resistors are fairly easy to match because we only have a couple of values here. And we can like do a layout for an R, do a layout for a 2R, and we can get there. It's a more complicated circuit and it's a little bit slower, but you can see here for each bit, all I have to add is another 2 resistors and a switch. So it's going to be a very compact design here. So the trick to analyzing this, and now I can go back to my other slides, is we're going to look at this network right here, and this is an R2R circuit, basically. If we look at the REQ, looking in right here, REQ1, we see 2R. If we look at REQ2, we see 2R in parallel with 2R, which is R, plus R, because it's in series with that, we see 2R. We look into REQ3, we see 2R in parallel with 2R, plus R. It is 2R. Doesn't matter where you look in this network, the resistance is going to end up being 2R until you get to here where you have 2R in parallel with 2R is just plain old R. Okay. We figured out the REQs. Now we want to figure out voltages using those REQs and the voltage divider rule. So this node right here has got to be at VREF because it's tied to VREF. Okay, now I go over here and I have a voltage divider that looks like this. Sorry, it's not AC. VREF. I see an equivalent resistance of R up here. So I see this R resistor. And this whole rest of this massive network is 2R in parallel with 2R, which is R. So the voltage at this node right here, by the voltage divider rule, is VREF over R divided by 2R. It's a half of VREF. Let's get rid of that circle. Okay. So the voltage right here is going to be Vref over 2. Once you know this trick, it's not so bad. And this one's on the homework. And it's on the practice final exam. And this voltage over here, my input voltage is Vref over 2. So I change this to Vref over 2. And I do that same calculation. So this voltage right here is going to be Vref over 4. And it just continues on. So this one must be Vref over 8. A miracle called the resistive ladder. Another useful circuit you should have studied in 188. As opposed to the, I don't know the mess of stuff that's in there. So the total resistance in terms of R is going to be, the equivalent resistance looking into this network is going to be R. No matter how many bits we have, the total resistance I'm going to have as far as resistors I have to build will be, I need 4R. Wait, that's the divider one. I need 3R per bit plus 4R. So 3R times N plus 4R would be the total resistance we get in there. It's not writing very well. Okay. So we're going to take this network, and now we can kind of get a clue as to how to understand this. I've got Vref right here. This is Vref over 2. And I keep on going down the line. We're going to do a 3-bit one, so we're going to pretend like this is connected and just make this Vref over 4. And then we have the actual diagram for a 3-bit converter. Vref over 4. Now that's a 2-bit converter. Is it 3? Oh, yeah. Okay. Yeah, you're right. You're right. This will work. Okay. Never mind. I missed something here. So this is a 3-bit converter here. Our Vref, we're given, it's 3.2 volts. And our R's are 2K. So this must be 4K. This is 2K. I don't care about that one. 4K, 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 4K. Now we want to set this up. Our most significant bit is going to be on this side. MSB. So our most significant bit is a 0. So we're going to take this switch and we're going to put it to ground. It stays right there. Over here, when I want to tie it to 1, I take B2 and I tie it into the input node of the op amp. So these are 1s. Now we can find the current in each resistor. Oh, what do we need to know here? You need to know what this voltage is. Someone, please tell me what the voltage is at the green dot. You're not, okay, I don't know. Every time I give the final exam in here, there is one problem where there's an op amp involved. And it can be a different problem from semester to semester. But I have one terminal of the op amp grounded, and one of the questions on there is what is the voltage at the other terminal of the op amp? And typically about 2 people get it right. It's the golden rules of op amps. If this thing isn't saturated, whatever voltage is on the positive node will be on the negative node. Whatever voltage is on the negative node is going to be on the positive node. Okay. So this voltage is 0 volts. And I was just grousing to Ben about this morning. If I want to find the current through this resistor right here, that current is going to be the voltage drop across it, Vref over 4. Minus 0 is the voltage on the other side. So V equals IR, I equals V over R. So we divide by the resistance, 4K. The current through this resistor right here, if that bit is on, will be Vref over 2 divided by 4K. R. 4K. The current through this resistor would be Vref over 4K. So what you get here, you can write a formula almost from what we just said, is that the current, the sum of the currents, I'll write a summation signal, going into the negative terminal node is going to equal Vref is common term to all of them. 4K is a common term to all of them. And we're going to make this 2K. We're just going to make this R because otherwise it doesn't make any sense to me. I'll explain that in a minute. We're going to make this Vref over 2K times B1, the most significant bit, over 2, plus B2 over 4, plus B3 over 8. That will be the current going into the node. The output voltage is going to equal the negative, because of passive sign convention. This is the positive side, this is the minus side. So the voltage across it is 0, because current's going this way, is 0 minus V out. V out equals the negative of R, and this was R, Vref over R times B1 over 2 plus B2 over 4 plus B3 over 8. And you could just make the resistor string a little bit longer, divide down Vref a couple of times, match your resistors. You've got a small compact DAC. Okay. You understood that. The last problem on the practice final shouldn't be bad. And also the stuff on the homework. So this is the resistor with the types we've looked at. We looked at the resistor string. You probably, oh great, doing this again. I have a magic button now. I have a button I can push. This is the binary switch array. The R2R, the one we just looked at, was the inverted R2R. And this is the R2R. And the only basic difference between them is where we're putting the switches.
Wait, the inverted one has the Vref.
It has the Vref. This one has the Vref. Well, this one has the Vref here. Yeah, and this one has the Vref over here. Whether we're putting the Vref on the switch or putting the Vref on the resistors. I have to buffer Vref. This one, you're going to have a pretty hefty buffer. Wait, why is this not working? This one you're going to have, if you connected this Vref to the outside world, your analog engineer would need to know that they needed to buffer Vref to make sure it was a stable signal. This one right here, Vref is, well, Vref's going to have to source current. So it's going to have current going out of it. This one, VREF, has to be capable of sinking current. So this thing has to be able to take current going into it. So it's a different specification. If you actually look at op-amp specs and read them, they're like, the electrical characteristics are like 3 pages long, but you get used to the things that are important. One of the things is that they will source, some of them will source 3 milliamps and be able to sink 8 milliamps. And sometimes it's the other way around. So you got to pay attention to that. It's not just how much current this thing is capable of using or supplying or sinking. It's which direction the current's going in will actually affect it. Okay. One more thing for 490 in the fall. There is a small error in the schematic. Thank you, Dr. Brower. We're missing this. Okay. We know inside of integrated circuits, and we do talk, there's a whole week on switch cap in 490 in the fall, but this is a switch cap circuit here. Inside an integrated circuit, it's really hard to build resistors. They take out a huge amount of area, so they're very, very expensive. Capacitors, I can build scaled capacitors fairly easily and in a much smaller space. I can build MOS capacitors all over the place. And so I've got those parallel plates in there I can build. So this is a technique people use inside of integrated circuits to actually design circuits with gain, any analog circuit you want, no resistors, all caps. They're called switch cap circuits, and I think they're amazingly cool. But there are 3 phases to this. So because capacitors store charge, the first thing, the gain isn't going to be constant. It's kind of like those dynamic circuits we looked at earlier, where you're only getting an answer to your analog question during half the clock cycle. The first thing we have to do is reset it. And when we reset it, we are going to basically discharge every single capacitor in there. So I need a switch, I need a MOSFET right here that's capable of shorting out the 2 terminals of this capacitor. During reset phase, we're also going to take every capacitor here and put them in the switch position shown. And in the switch position shown, this 8C capacitor is going from ground to VZ, which is also by the miracle of op-amp rules, is also going to be at 0 volts. So no voltage across any of these capacitors. All of these are going to have Q equals 0 during the reset phase. Let me write that up here. During reset. So this is our starting point. We've gotten all the charge out of the circuit. Okay, now we're going to switch to orange. I like orange lately. Okay, we're going to open this reset switch, and for all the BIs that equal 1, we're going to move their switch down from ground to VREF. So let's say this capacitor right here is the only one that's a 1. I move B2 to VREF minus VREF. So B2 is at minus VREF. Now I have a capacitor with minus VREF across it. Its charge is going to be Q equals CV. Q equals CV. The C is 4C, and the voltage across it is minus VREF. So I put some charge across here. This switch is open. The charge is going to flow, just like current flows. The charge is going to flow into this capacitor and give it a charge of Q equals 4C over VREF. So the voltage across it, its Q is 4C over, the sign switches because the polarity switches. This is plus and this is minus. 4C V ref. Okay, and the voltage across it, Q equals CV, sorry, will be Q over C. So the voltage across that capacitor will be Q over C, 4C V ref divided by 16C. The C's cancel out if they're scaled correctly, and you get 1/4 of full scale from that one B2 bit. Okay. And then your DAC is out, and then you put some kind of storage thing on there so that kind of like a PWM circuit, so that you, because it's only good for half the cycle. It's 0 for the other half of the cycle. Okay. What do we do now? Okay, so we've got this 4-bit DAC. VREF is 1.6 volts. My B, draw this little thingy back in again. B is 1001. So our most significant, let's look at this. This got multiplied by 4C. If it gets multiplied by 8C, I'd have a bigger number in here. So in this case, because capacitance is like inversely proportional to impedance, I'm sorry, and you can look at this formula too. This is going to be the most significant bit. Because if I put 8C there, this 4C would become 8C. I would have a larger voltage on the output. I would have half full scale. It's exactly inverted from resistors. Okay, so my most significant bit in this case is right here. And that's shown going to B1 too. I did get that right. We're going to put B1 in the 1 position to VREF. B2 goes in the 1 position. B3 stays where it's at, and B4 goes into the 1 position. The total charge on the input is going to be minus VREF Q equals CV times the capacitance, and they're going to add together, times C plus 4C. Oh, wait, this thing is just skipping. 4C plus 8C. So this is the charge on the input. My charge on the 16C capacitor, it's got to equal, because it's going to, the charge is going to equalize across there. We're going to get its charge. This will be it. Wait, what? I just did this. Q equals CV. The voltage across, yeah, I just explained this. The voltage across this capacitor will be V out. VREF times C plus 4C plus 8C is 13C, all over 16C. So as long as I can scale those capacitors correctly, and you notice I said as long as, we built a DAC like this. We built an ADC like this. It was kind of like this in reverse. And it relied for accuracy on being able to scale. We wanted to get 10 bits. So we had to have a C a 2C all the way up to 2 to the 9th C or something like that. We had to go across a wide range of capacitor values to get this small ADC that we could fit in a 30 micron wide space, and we could make it as long as we wanted it to. It ended up being like a centimeter, 30 micrometers by a centimeter. And 10 bits.
Oh.
And the reason why it had to fit in a 30 micron space was because there were 512 of them in parallel. Okay. I just showed people a picture of it in 490. Right, we got that. This is the problem. This is what they had started to do, and this was like my first assignment at JPL, was look at this ADC and see why it doesn't work. Well, first I'll test it and see how many bits it has. And I said, okay, it's a 10-bit ADC, but the last 4 bits are garbage. It's good to about 6 bits. And the thing is, your eyes, the dynamic range on your vision is only about 6 bits. So the pictures look perfectly fine. But if we want to use this for any scientific imaging or to like drill down and look at the picture and figure out what's going on in finer detail, we couldn't do it. So the next thing was fix this. So what the problem was is the guy who laid it out, what he did to get the capacitance, he said C equals epsilon A over D. If I make something that has exactly twice the area, I'm going to have twice the capacitance. If I have exactly 4 times the area, and he just kept on scaling it down like that, that does not work really well. There's a problem going on in here. Remember when we talked about overlap capacitance? Okay, so the edge effects of this capacitor, I've got a capacitor that looks like this, but the perimeter of this is going to determine, and there's another plate down here. The edge effects, there isn't just capacitance across the area you intended there to be. There's going to be little fringing fields across here. You should learn about this in 364. I had a whole year of BMAC, plus the microwaves classes. Okay, but there's fringing capacitance across here. It doesn't look just like the ideal parallel plate capacitance. There's capacitance on the edge. So you have to worry about the perimeter to area ratio of these. So this was where we went to get to 10 bits, is if I want 1C, I use a capacitor like this. If I want 2C, I use 2 identical capacitors. They have the same perimeter to area ratio, so they have the same fringing capacitance, and I connect them in parallel. If I want 4C, I use 4 identical capacitors, and I can connect them in parallel. So this was the next step we did, and we got down to about, well, I called it 9.5 effective number of bits by the time we were done with that. You can go beyond that and do a little bit better. And I don't know, I honestly have never seen this because I haven't had to do it. I've had to do this. This is called a common centroid, where you have, this is C. If I want 2C, I connect across like this. If I want 4C, I connect across like this. And again, this would have been hard to fit in a 30 micrometer pitch, is that I keep it so that these 4 capacitors have a common centroid to them, and that helps even out the fields even more. Again, for a higher level of accuracy. This would be for something like a commercial product for TI or analog devices. For us, when we got to 9.5 bits, we were overjoyed and we said, look, it works. Mars people, fix it. It was almost that bad. We had an user interface that looked like a checkerboard. The white squares were on and the black squares were off. And I could look at the pattern on the checkerboard and literally tell what state the imager was in. Needless to say, we had to teach all this to the people who are going to use our cameras. We had a non-standard serial interface on it, and I inherited it and it worked. I had no reason to fix it, but the Mars people were not too happy with it. It wasn't something like USB or standard UART was the word terminology then. It was just our own little made up thing. This is our serial interface. So they had to build basically an FPGA to interface with a camera. And I am the one who had to sit there. I wrote a really nice document on this is what we did. This is the only 25 milliwatt camera in the world with 5-wire interface. You get to use it. And so they had an FPGA guy who did the interfacing for us. I just explained to him what to do, like I always do with FPGA. It's been my, oh, somebody moved. No, that's fine. Keep the lights off. So if we try to do a C2C with this, we have a bit of a problem. In our reset phase, we have to ground all the capacitors to get the charge out of there. Eventually, with time, electrons find their way into that capacitor and either charge them or discharge them. So they're in an unpredictable state. Now this capacitor, we can switch to ground, and this node's at ground. We know that, it's our virtual ground. But this capacitor, that node we can ground right here. This is a floating node. I have no way to ground that node. What I would have to do here is I would have to put, we'll talk about this when we get to integrators in 490. I have to put a capacitor across there with a switch to discharge each one of those nodes, and it just adds to the complexity of the circuit. Yeah. So generally not all that great of an idea. It is much simpler to use this. But that's binary weighted. The disadvantage is we have to do all that common centroiding and make sure our capacitors actually scale. The advantage to this one is all the capacitors are the same size. A little bit easier maybe to get down to a few number of bits, but we have to put a few extra MOSFETs in there. I don't want to talk about this.
Delete the slide.
I normally just don't talk about it. It's BJTs. The issue with this that's somewhat interesting is that this one is not guaranteed monotonic because the monotonicity depends upon the scaling ratio of these resistors. That's the only interesting thing I have to say about that. Yeah, and I only ever had to design schlocky electronics inside of integrated circuits. I wasn't doing professional stuff. Well, I was doing professional stuff, but it was just had to be good enough so we could say it's 9.5 bits. Mars guys, Martians, go fix it. When you're the only person in the world who has a 25 milliwatt camera, people will do whatever you tell them to do. And they will bring wheelbarrows of money to your door to buy this thing because nobody else has it. And you can, oh, it's even more amazing. We built a rad hard camera.
A what?
Radiation hardened camera.
Oh.
If you're out in space, like if you have a satellite application where you want to send something to Mars or Jupiter or just any place off this planet, you don't have the Earth's magnetic field protecting you from radiation anymore. And electronics are very sensitive. You get ionizing radiation coming into them. There's some devices, they will, you get a high energy, you can get high energy event coming into them. They will completely wipe out the whole device, destroy it. With memories, a lot of times, lower radiation will do things just like change all the bits in your memory. And higher radiation may go through and destroy individual memory cells or blocks of memory. So when they put stuff in satellites, a lot of times what they have to do is shield it. Put a big shield around it so that the radiation can't get through. Shielding's heavy and you have to launch it up in space. It takes like 5 pounds of fuel to launch 1 pound of stuff. So the costs really add up quickly. They want to keep the weight down. If you have an imager, this is something that has to put light in by its nature. You have to put light into it. You can't shield it. You cannot put a big block over it. So what we had was we had imagers that were able to take high doses of radiation and still operate. Sometimes we got some really weird pictures in space. And one guy took that idea of like, oh, you're getting these pictures of this ionized radiation in space. Can you build me a camera that will do this? And he was from Johns Hopkins, and he showed up, and I talked, and I was the designated astronomer of the group. So I went and talked. I can speak Namer if I have to. So basically, what he wanted was he was looking for these high energy photon events coming in, and they happen and they occur in like 200 nanoseconds, or they're done in like 600 nanoseconds or something like that. So what we had to do is if we detected a high level of signal on anything in the array, we had to immediately go and add 5 to that signal address and create this 5 by 5 window around the invite, and take pictures really fast, just pictures after pictures. And so he could go in there and zoom in and see what was going on in the event. I had to build an adder that could add in what at that time was less than a clock cycle and settle, and it was a 10-bit adder.
Yeah, that's what makes it more impressive.
Okay, yeah, okay. But again, he had suitcases full of money, so we were willing to do this for him. He didn't have wheelbarrows full of money, but he had suitcases full of money. We were willing to spend the time. He could afford us. We weren't cheap. Our software tools cost $250 an hour at the time. So he could feed our Mentor Graphics habit. Mentor Graphics has come down in price. And we want to look at A to D converters. This is the most useful ADC converter that you can ever learn about. This is the one that gets used the most. This is what I like to call a one, and this is a, try the other button. Fingers work, no. My thingy's not working. Now it will. Okay, so this is what I like to call a 1-bit ADC. And we use this a lot. We use this with, we have this arbiter prop thing in the lab where we say, okay, is this voltage level, we pick 2 points in our that we're reading at random, and we say, is this voltage level higher than this voltage level? And 2 different bits, and we say, okay, if bit A is higher, we're going to call it a 1. If bit B is higher, we're going to call it a 0. If they're too close, we're going to call it a trit. It's a 3-state logic thing. Okay, so what we're going to do here is we put 1 voltage on here. This can be tied to a reference voltage in the simplest example. If V plus is higher than Vref, V out's going to equal 1. If V plus is higher, greater than V minus, V out is going to equal a 0 if, that does say if up there, V plus is less than V minus. And in our case, V minus is Vref. So we can set the reference level and we can tell if this is higher. If it gets within, depending upon how good your comparator is, If it gets within 50 millivolts or so of being close to each other, if this was 3.2 and this was like 3.25, there's a chance you end up in the linear region and you get a value between 0 and 1. So you want to have a good V offset on that to get that to work. Pretty amazing how much that circuit gets used. This is a review. How much time do we have? Oh, good. Okay. This is a review. This is an ideal ADC input. If I put in anywhere between 0 and let's crank it again. If I put anywhere between 0, try the button. Yay. Okay. If I get anywhere between 0 and 1/2 voltage VLSB, this is my analog axis. This is my digital, my output. I'm going to call it a 0. The next one VLSB, I'm going to call it a 1, etc. And we looked at that before. The way we calculate what our predicted digital output is we find the portion of our input signal. This is the input. It doesn't look like it from the diagram, but believe it or not, that's the input. We find the fraction of our input signal is how many, no, this isn't the fraction. How many LSBs we're getting out, how many voltage LSBs. So it's like 1/2 volt and an LSB is 1/10 volt. That would be 5. Our full scale, you know, our predicted answer would be 5. We round it to the nearest whole number and we get our output. You can also do this, calculate VLSB as being 2 to the n over V full scale, and just plug that in if you don't know what the voltage of the LSB is yet. And we did those calculations in the last class. Okay. Now there's different ways, okay, it's an analog to digital converter. There's different ways we can determine the number that we want on the output given a voltage on the input. We could go through and test this analog voltage versus our predicted analog voltage at any given point. So I could just go in there and say, okay, this is 1 LSB. Is it bigger or smaller than 1 LSB? Do a 1-bit ADC on it. And I answer that question. I go, this is 2 LSBs. Now the problem is if I have a 10-bit converter, I'm going to have to do that 1,000 times, 1024 times. And it's just not going to work really well. It's going to be slow. Highly accurate, but kind of slow. Okay, now I could do something like a binary search. Now this is like a successive approximation converter. I can get that word out eventually. And this is kind of like the game we used to play when we were kids. And I say, I got a number between 1 and 100. And the only thing you could say is, okay, is it bigger than 50? Or is it less than 50? You could ask one question. And they'd say, okay, yeah, it's bigger than 50. And so I said, so the next number, I guess, is 75. And then I go half the distance, you know, each way, and I get there eventually. That's a binary search. I'm going through and I'm picking out, okay, if my most significant bit is 1, and I run this into a 1-bit comparator, is my input voltage greater than or less than 50%? And then I pen down the value of the most significant bit. And then I go to the next most significant bit, which is like worth 1/4 full scale. So then I determine whether it's in the lowest quartile or the, you just kind of like go through and do that. And then we'll do that. So this is faster than the linear search. But if I want to get this really fast, I'm going to use something like a flash converter. This is the keyword you're looking for if you want a really fast one. I basically test all the possible combinations of the bits all at the same time. And I find the one that works first. It's going to be a much bigger ADC, but it's going to be extremely fast.
Wait, can you speak that again?
I'm going to test every possible value at once. So I would need, okay, so like a typical design, you have like that resistor, you have the voltage coming in. Here's a really sloppy design. I have a 10-bit converter. I have 1024 comparators. Every single one of them has a different VREF that corresponds to all zeros, a 1, a 2, all the way up to 1024. And I do all the comparisons at the same time, and I find out which one, where it stops tripping.
Where it stops tripping. Okay. Yeah.
Well, they'll be, let's say it's, if it was like directly, exactly at half. The comparators on the bottom would be all being reading low. The comparators on the top would all be reading high. And I just look at the place where that changes, and that becomes my answer. Extremely fast, extremely power hungry, and extremely big circuitry. But yeah, they wouldn't fit in a 50 micron pitch, a 30 micron pitch. So we're going to look at some topologies here. There's a lot of blocks in here you could easily build with Verilog. But we would have to build, I'd have to build them with schematics because I'm challenged. I put my input voltage in here. What I did is I just built a counter and I just used it over and over again. And then became kind of like Verilog. Plopped down a picture of my counter. Here's my input voltage. I want to compare it to something. This is called a counting converter. I've got this flip-flop here that's going to flip when change states, when it's going to be 0, it's going to start out at 0, and eventually when it hits 1, I'm going to say I'm done. When the comparator goes from 0 to 1, I'm going to be done. I take this flip-flop output, and it's normally 0, and I've got the clock going in here. The clock feeds a counter. This counter starts at 0. And I put in 0, and I need a DAC in here too, by the way. I take the 0, all zeros, and I feed it into the DAC, and the DAC produces an analog voltage with which I'm going to compare to VX. Okay, VX is higher than 0. So I go in here, my flip-flop doesn't change state, my clock keeps on clocking, and on the next clock cycle, I increase this to 1. And then that is going to cause my DAC to go up a little bit, and I compare VX to this new slightly larger voltage. This is a linear search, by the way. This is a slow one. And it doesn't match, so I go back into my flip-flop, I count another clock cycle, and I go back through. So this is like a system block diagram. It doesn't have all the circuits in it. How long is it going to take to convert? 2 to the n clock cycles. On average, well, on the average, actually on average, it's going to take 2 to the n divided by 2 clock cycles. But sometimes it'll take 2 to the n cycles, sometimes it'll take 1 clock cycle. When I get done with this and my flip-flop says, okay, I'm at my end of conversion, then I send that data out to the outside world. That is the counter count at that time is what I've converted. So basically what I'm doing here is every clock cycle, I start out at 0. I go up a little bit more in voltage. Okay, thank goodness. Okay, and I go up a little bit more in voltage, and I keep going up a little bit more in voltage. When I get to here, I say EOC. And that would be a 5. It's always going to give you a count that's a little bit higher than your ADC output, but that's no big deal. Okay. I hate them. I hate them. Negative logic people. Okay. This is the way I would do it. And Jack was the first one who looked at this and goes, Julie, it's just the inverse of what she did. And I go, yeah, of course it's Dr. Brown. As soon as I heard it. The way I would do this, and I've actually done this, and this is my algorithm, positive logic thinking person, is this is a successive approximation converter. The one we just looked at was a linear search. This is a binary search. So I've got a 3-bit converter. I'm going to guess 100. I'm going to set the first bit high. And then if that isn't high enough, I'm going to do this. My next thing would be to guess 110 would be my next highest guess. And if this was too high, I would guess 010. I know the first bit is a 0. I'm going to guess the next bit. My next guess here, if this is too low, would be to guess 111. Look, I get there in one clock cycle list. If this was too high, I would guess 101. And then I'd have to determine whether it was 101 or 100. 011, I would guess the next bit. If this was not high enough, I would guess 011. If it was too high, I would guess 001. And I would use the next cycle to kind of get zoom in on that last bit. So 3 clock cycles, 3 bits. If I want to do a 10-bit conversion, it's going to take me 10 clock cycles instead of 10 24 clock cycles. So this is significantly faster. And let's see how we implement it. So here's my successive approximation implementation. A lot of block diagrams, like 490 in the fall. Sign up for it. It's a good class. How many times I have to say that? Try doing this. Wow. Okay. That only took me like a lot shorter than it used to take me. I put in my analog input voltage into here. It's going to be compared to something. What we compare it to, we have to have this little state machine in here. My successive approximation algorithm, or whatever SAL stands for. This is going to be what generates what my next guess is. So I'm going to I start out at 100. I set my DAC for half full scale. I compare VX to half full scale. Is it higher or lower? And then I set the next bit. So the way this would work on here is, this is an 8-bit, so I have 1, 2, 3, 4. I would guess on the first clock cycle, I'm at 100. That's too low. So the next one I would guess 110, and that is 6. So I have to go up 2 little tick marks. So I would go up to here. And that is too high. So my next guess would be 101, 101, which is 5. So it would go down to here. And yet that is still too high. So then I would guess, we already know 100 is too low. So we know the answer here is between 100 and 101. And you can set up your algorithm to pick one or the other. You still have that quantization error in there. You can get there in 3 clock cycles, worst case. N bits, worst case, you can get there in N clock cycles. Way, way faster. A little bit more complicated because I don't have that simple counter in there. I've now got to set up some kind of logic in here that needs to look at that bit and determine what the next guess is. Not too hard to build, but a little bit more complicated than a counter. I love counters in FPGA.
What happens if exactly right.
If it's exactly right the first time, you don't know that.
Yeah, it was like.
Yeah,
exactly.
it's still
So
gonna
when just bring
take,
it
it's still
higher,
gonna take you 3 clock cycles to get there.
So, okay.
Yeah. Because you have to go, you know, you were pretty close on the first guess, but you
But
didn't
you
know
didn't
that.
know. So it would give you higher or lower.
Right.
And then it would just be like higher,
Yeah,
lower,
yeah.
lower. And it's like, wait a minute, I'm back where I started.
Right, exactly. That
So-
can happen. So you can't get there in 1 clock cycle. If you want to get there in 1 clock cycle, you have to use a flash converter. But I think I'm about done for the day is what I decided. We could look at this. We could, oh, do I really want to look at this? This is the circuit that was Sharber's favorite. This was John Sharber's very favorite ADC. And he would get the students to build it.
Oh, yes, I do remember that.
Okay, and I would tell him every single time, you know that circuit doesn't work. And I'd explain to him why it doesn't work. And I go, you need a negative power supply. And he's like, the students don't know how to do negative power supplies, Julie. They don't understand negative voltage, Julie. Don't make it. For people like you would be okay with that. But there's like, there are people that just can't do it.
No, yeah, it was like when I first started, I think it was the 286 we got my ADC.
Yeah.
And then I was like, what's the problem? And then I accidentally made a negative power supply and that fixed it. I was like, what happened? I didn't learn until later. I was like,
Okay. There's this guy who's he's actually really smart and he's gone really far in engineering and he graduated about 8 years ago. I won't tell you who he is because you'll know instantly. He got me to write this analog class for him back when I actually had free time, as in I had time to write curriculum. And Dave Scott supported this and everything, and this is what eventually evolved into 490 in the fall. But his first setup, he had to take this op amp and power it up with plus and minus 15 volts. So he gets it was plus and minus 10 volts. So he doesn't have a plus and minus 10 volt supply on the breadboard, and he has to wire this thing up using 2 power supplies. And what he does is he comes up with this brilliant idea of, I'm just going to take it and I'm going to crank it up to 20 volts. And I'm going to put the positive terminal on the plus side, and I'm going to put the negative terminal on the minus side. Look, it's the same thing as plus and minus 10 volts. And I had to break it to him that all those bypass capacitors that are grounded are now no longer connected, and they're like antennas, and your whole board is like really noisy. And then about 5 minutes later, I was trying to connect it up, and I blew the front end on that board, and Sharber fixed it for me. It was the good old days. There was smoke, but I did it. I know. It was okay. The guy didn't feel bad. And he's now doing all kinds of cool stuff. I don't want to talk about this. I've got 5 minutes. I can't finish this. Yeah, let me just say it depends upon the exact value of RNC, the slope of this. And we'll get to this on whatchamacallit, Tuesday. And if you get a resistor out of the parts cabinet, it's going to be probably 10% around here. You can buy 0.01% precision resistors. You could get what this rate was down pretty good like that, except for the capacitors. Capacitors are plus or minus 20%. You can't do much better than that. And the whole timing and the entire accuracy of the circuit depends upon knowing the exact value of RNC. We need that second ramp, that downgoing ramp, to cancel that out. We'll talk about that on Tuesday. I've just gotten way past where I wanted to go. Okay. Any questions? Anybody I missed? Let me just stop my sharing so I can see everybody. Let's see who's here. Who do I have not here? Oh, you're Gabe. No. Mouse. Okay. Victor. And Chris. Okay, I got it. If you watch the video, send me an email, let me know. Okay. I'm gonna stop recording. Take 490 in the fall. It's better than me teaching 188.
I have a question, Julie.
Yes.
For doesn't 490 have a lab?
No. It's a 3-hour class. The lab is our class time.
Okay, so is it 4 credits or 3?
It's 3 credits.
Okay. If you take, like, let's say 3 senior electives with labs that are 1 credit, would that count as like an extra class?
Yes, it would, but the senior electives don't have labs.
None of them have labs? Oh,
All the senior electives are 3-hour classes.
okay. Thanks.
Okay. Even like 484, which is actually has a lab associated with it, what they do is they only meet 2 days a week for 50 minutes, and then you have a really long period on the 3rd day of the week. I just do it all in 50 minutes, and we just talk. I just talk less. Some days I talk 10 minutes. If I can get you guys on the bench.
That makes sense. And for making up one of the lab quizzes, could we do it during office hours, or should I do it during lab tomorrow?
Yeah, either way.
Either way.
Yeah, I'll be there. I'll bring my hard drive with me.
Okay.
Okay.
Yeah, that's all I have to really ask.
Okay. Okay.
Oh, also about the pre-lecture today, I tried those tips that you gave me and they didn't work.
Uh-oh. I will look at it, okay? Just send me an email and I'll look at it. It could be, a lot of times it's just rounding error. And if that's the case, if you're off by, if you're right to like 2 significant digits, I just give you credit for it.
Or with it might be a negative error.
There are sign errors too. Yeah, that's
negative.
okay. Michael's saying the voltage was negative on one of them, so it might have been a sign error.
Yeah, no, I had a negative for the first one, so I don't know what I did because it was pretty clear cut. But
Okay, I can't tell you unless I can see what you did. So.
All right.
Okay.
I guess I could just ask you about it tomorrow since you'll be able to look at it probably.
Yes.
Then.
Right.
Okay.
Okay.
Thank you.
Okay, I'll see you.
This is what I heard Max say.
Okay.
So, Julie,
Yes.
I need help with the lab if you can, like for 5-10 minutes.
Okay, maybe. As long as it's short, because I'm getting tired. Amelia has a question, so hold on. Yes.
All right.
What I heard Max say was, you learn in the lab for is just the drawings, right? Everything else just on Linux.
If that's what he said, he's the one who's grading it. Okay.
Yeah, I was like, oh, you have to turn it in after that.
I usually say like formal lab report. If you actually put in your lab report that the drawings are in BB Learn, that's fine too. People stop complaining as much about having to put the schematics in their lab report when I stop making them print them out. Because then it's cut, paste, and send. Okay. All right, Jacob, what's going on?
I will share my screen.